Okay, now there's something really important about exponential functions and their applications. We got to really understand. Okay. It goes back to the table we made last time. So ask people, or some people remember what to do. And some people almost remember it. Okay, there are steps in understanding this. We want to get it down. Okay, so how do we get the new amount from $1,000? Okay, well, we take $1,000 and 10% of $1,000. Okay. Then whatever amount we get, we're going to do the same thing with that amount. We're going to get $1,100 in the next step, and we're going to take 1,100 and add 10% of the 1,100. So we're going to get a little more interest than we got the first time. So we can see that in the way we build it up is, well, that's then $1,000. Plus 10% of $1,000, and 10% 0.10. Everybody's got that down, and that equals $1,000 plus $100 equals $1,100. Okay, now that's more cumbersome than it needs to be, but we have to understand that that's what we're doing. Now we can shortcut that because we notice $1,000 plus 0.10 times $1,000 equals $1,000. We're going to factor that $1,000 out of these two terms. We've got $1,000 in common here. We can go backwards on the distributive law, and we can write this as 1 plus 0.10. Okay. Then we can confirm this. Distributive law going forward. This means $1,000 times 1. Well, there it is, right? And $1,000 times 0.10. And there it is. And of course, then we can add the 1 and the 0.10. Okay. This is a critical step here. Factoring out that 1,000, so we understand why 1.10 times 1,000 cuts through all the details of this calculation. So new amount is going to be $1.10 times $1,000. I'm going to write it out like this. Okay. There's my $1,100, but I'm not even going to write out 1,100. I'm going to write it out as 1.10 times $1,000. I can always calculate that very easily. Okay. Now, we're going to add 10% of $1,100 to $1,100. And we do that. We can always do 10% of $1,100. It's going to be $110. Now we're making $10 more in the second year's interest than we did on the first year's interest. Might not seem like much over a year, but when this starts accumulating, it's going to be quite a bit. Okay, so we add 10% of $1,000, $1,100. And what do we get? We get 1.10 times $1,100. We have to understand when we do this, that we're just shorting, that we just shortcut this. Adding 10%. $1,100 is just be 1,100 plus 10% of 1,100. When you factor out the 1,100, that'll be 1,100 times 1.10, 1,100 times 1.10. Okay. I'd say that right. I think you see it. Okay, so I'm going to write this as ahead of myself. And so it's $1.10 times this. Now, of course, that's 1.10 squared times $1,000, and that's why I'm going to write it down here. Well, now we're going to do the same thing. We're going to add 10% of this. We don't have to calculate this. We can simply write out what we get, which would be 1.10 times 1.10 squared times $1,000. And of course, that's 1.10 cubed times $1,000. And then we're going to add 10% to that. Then we're going to keep doing that, and we don't have to write it out. We want to find out what we have after 750 years. We don't have to write 750 columns, which will take us most of that 750 years. Okay. We can set a rule. After n years, it's clear that we're going to have multiplied by the 1.10 n times. Why do we have a 1.10 cubed here? Because we multiplied by 1.10 here, then here, then here. Okay. So if we go down to n years, we'll multiply by 1.10 n times. That's how much we've got. And right there's our exponential function. So A is the amount. As in roughly years, it's 1.1 over the n times $1,000. Now there's something else we can do with that expression. But we want to understand this, and we want to understand why it's 1.10 and not 0.10. Terminology in your text, if I remember the words to use. Words I've always used, I think are good words, is 10% is the rate. It's the interest rate. It's not a rate of change, it's an interest rate. And the 1.10 is your multiplier. So call this the growth rate. Most authors do. It's a pretty standard term. So if you haven't seen it in open math, well, you can call it whatever the equivalent is. They call it, maybe they'll just call it the rate. I want to put growth in front of it so we don't confuse it with a rate of change. Because I use growth, and well, I was hoping they did. I didn't see it when I was looking at the homework, because what you get in the homework is different people doing it different ways. Okay, I've just written somewhere between 100 and 150, 200 problems. I haven't put them into the main bank because I think a little bit differently than they do. Because of what I should see my students need. Okay, I'm dealing with different students. And I'm not even going to share them, but put them in the overall bank. Don't want to confuse my colleagues. Don't want them bothering to look at stuff I'm writing unless I know it's something that's pretty interesting. Okay. And some of it is, some of it will go into the problem. Okay, well, anyhow, you got the growth rate. That's what I'm really getting at. Growth rate. You've seen that terminology. Okay. Not a rate of change, it's a growth rate. So I'll just put a little note here. That can be a little confusing because you got rate used here and you got rate used here. The rate of change, just think fundamental triangle slope. Okay, or changing this divided by changing that. That's a rate of change. That's not what this is. It's a multiplier. Well, it's not a multiplier. It is what you multiply by whatever number you got here to get the change. Which makes it even more confusing because you still have a change going on. Okay. Then we call this the growth factor. See that? I don't know why it's talking about growth rate. When they talk about growth factor, they call it a multiplier. It's at least what I see in some of the problems. Okay. So you have problems where you're given table tells you, year one, year two, year three, or whatever, day one, day two, day three, whatever you're measuring, it gives you three numbers there. Okay. It's like you have a table that gives you 1100, 1221, 1331. Okay. Sorry. 1000, 1100, then 1221, then 13. Okay. And from that table, you determine what they call your multiplier and then your rate. You have to understand the difference between a multiplier and the growth rate. So in this problem, 0.10 is the growth rate, 1.10 is the growth factor. This is how much interest you get or how much amount grows by. This is what you multiply by to get the new rate. So you don't have to calculate the interest rate, the interest separately and then add it. Okay. We're not doing this. We're shortcutting it and we're doing this. So right here's our growth rate, our growth factor, and right here's our growth rate. Or they call it a multiplier. Well, that's what a factor is. A factor is a multiplier. Factor something multiplier. Okay, so multiplier is not a bad word. Clarifies what growth factor means. So my advice is understand both these terms. Understand why they're saying the same thing. Okay, so I see on the homework for people who confused this with this. We're gonna really understand this stuff. Okay, so now we have added 1.1 on time to the end times 1,000. We raise the growth factor or the multiplier in the end. If we compound twice a year, then we're going to do half of the 10% for twice every year. And that gives us a significant, small but significant advantage over what distance grows faster. So I'm not going to re-explain that. You might want to go back and read it. Okay. I'm not going to re-explain it because it's like a process this. Make sure you understand it. Now, if you have you can construct a graph of an exponential function. Now, if you just draw one freehand, you're not likely to get it right. We did that last time. I don't know how I did this time. Let's see. This thing doubles from here to here. Then it doubles again. From here to here. Like I didn't do too bad. It's a little longer than this, but maybe a little higher. No, it's about that. Okay. So it's not a great exponential function. But if you do your toolkit exponential function, you're going to get two doublings to the right of the y-axis. Because your exponential function goes from 1 to 2, and then from 2 to 4. And of course, you really have to understand that toolkit function. Okay, you just have to be familiar with how that works. So this is 1, this is 2, and this is 4. Right there. If you've got a well-scaled x-axis, you've got a usable curve to estimate. And you've got a picture in your head that helps you see how this money's going to grow, or how this population is going to grow, or how those bacteria in your refrigerator are going to grow when it warms up. Okay. You can then, notice I didn't label this. You can label it any way you want. Well, what I want to do is I want to label it by its doubling time. Okay, so I'm going to model this. And I'm going to model it by its doubling time. So we've got to do a little algebra to get the doubling time. Now, this could be any two values at all, as long as the second is bigger than the first. But $1,000 and $2,000 for this function is simple one that we could use. Okay. Now, What's the value of N when A of N is $1,000? You know, I've been writing. Okay, not all that much. You know, inside of the board, it's not visible on the screen. Okay, well, you know what this is, you know what this function is, you don't really lose too much there. And I just wrote this, so here it is again. Doubling time, A of N goes from $1,000 to $2,000. What's the value of N? A of N is $1,000. And then what's N with A of N equals $3,000. The difference in those values of N is the doubling time. Because that's how long it takes to double. Well, let's answer those two questions. Can you tell me what the value of N would be when A of N is 1,000? And can you tell me what the value of N would be when A of N is 2,000? Let's move in. Okay, go ahead and see if you can answer those questions. First one isn't too hard. The second one, you got to remember what to do. So first of all, what's N when A of N is $1,000? Now, this is something you just kind of want to make sure you understand. What do you get if N equals 0? You get 1. Very good. And what's 1 times $1,000? Right. So that's why I say $1,000 to 2,000 is convenient. I pick the initial amount. And let N equals 0, I got $1,000. And then I ask myself, how long does it take to double? Okay. So. Okay. So, $6,000, because that's A of 0. This is function notation. That means the amount at 0 time. Okay. And then we pick $2,000 because that's double. And it's double 1 time. That's why the N that we get, the change in N, is going to be what we call the doubling constant. And that's going to relate to the graph because that's the number we're going to put here. Okay, so on the graph, we're going to put 1,000 right here. So we're going to put 2,000 here. And we're going to put 4,000 here. We just don't know what number to put here until we calculate the doubling time. So to calculate the doubling time. Yeah, A of n equals $2,000. Well, A of n is (1.1) the n times 1,000. So A of n equals 2,000 means 1.10 to the n times 1,000 equals 2,000. Now, how do we solve this? Well, this is very easy to solve if you remember how to change from exponential to logarithmic notation. Or form, actually, form with the logarithmic form. We first divide both sides by 1,000. Then we get 1.10 to the n equals 2. So log base 1.10 of 2 equals n. Now we went over this before, but don't expect necessarily that this conversion is all that firm in your mind until you've done a bunch of them. I'll write it out for you. The way I write it is first I write b to the a equals c. That's something raised to power equals some other number. And that's what I've got here. In this case, b would be 1.10, a would be m, and c would be 2. You can't solve this equation with rules of algebra that you've known up to this point. There's no way you can isolate that in. Can't do it by adding, subtracting, and doing so. Yeah, you switch it around. Okay, and you switch this around by the rule that says this is equivalent to saying that the log base b of c equals a. And that's simply if you have the graph of an exponential function, you switch all the x and the y values. This is equivalent to swapping the x and the y values, taking the table, say, of your basic exponential or your toolkit exponential function, and flipping the columns. That gives you the log base 2 function. You get log base b. Well, you've got this rule. Okay. And I could explain this rule in terms of transformations, but I'm not going to, because I'm afraid that goes over most people's head. I'll mention it in the calculus class. Still going to go over most people's heads, because it's a little more abstract. Okay. But the people who are like going to go on and be engineers and stuff like that, it's absolutely worth them seeing. But I'm not going to bother you with it right now. Hang on a second. Oh, you're going to go for engineering, right? Yeah. So it's worth seeing. Because I get second year engineers in my physics and molecular calculus and different equations classes. You have deficiencies at the level of pre-calculus because pre-calculus is not being taught to the level it should. Right? Now, I mean, I have down the road smart people that don't have those deficiencies, okay? They're not necessarily crippling deficiencies, but they're going to understand their engineering better if they don't have raised petitions, it's okay. They still do okay. They're doing good. It's things I wish they understood from pre-calculus, okay? So try to teach pre-calculus, at least give reference to the actual level of the course. Okay, well, anyhow, log-based VOC, and a philosophical digression. And you also have log-based VOC is log C over log B. Now, log C over log B is just a vertical stretch or compression of L of G. Log B is a fixed number. Log of C, regard C is variable. Take the graph of this and then vertically stretch or compress it according to reciprocal of log B. And there it is. And that's what I said in the same pre-calculus. I only took 30 seconds. There I go. Went ahead and okay. That just relates things to transformations. Transformations are very important. Use several examples in physics about things people don't understand because they don't have picture transformations. Back to this, well, that's going to be really easy to calculate. So now we have n using this one is the log of 2 divided by the log of 1.1 of 2 was the original z. Okay. And you do that, and it's approximately, I think I remember from last time, 7.2. Now, if you've got a button on your calculator, it'll do log, base, whatever, with just one button. I don't like that button. It bypasses the whole image of how the log function gets stretched and compressed according to your basis. And as I said, that stretching and compressing is very important for understanding a lot of things. But for people who aren't going to become engineers or go into finance or heavy duty mathematical business, probably never going to make any difference to them. Okay. Still, trying to teach them calculus. Okay. Well, this is a support place. So you have one person who's smart engineer. So I'm going to add a little bit of color to the thing. Okay. So now we got our doubling time. Approximately 7.2, so we can put 7.2 here, double that, 14.4. And if we wanted another doubling, we don't have room for it. It goes all the way up to here. We could put 21.6. Okay. Or a more accurate version. Then we have a picture of our exponential function. Okay, I was actually going to say this, but I didn't have a lot of room down here, but the question came up. This is also equal to the natural log of C or the natural log of B. It doesn't make a bit of difference which log you use when you do this. Okay. Now, the one place the natural log becomes important is you can have continuous compounding or continuous growth. Okay. You got bacteria growing in your refrigerator, it's pretty much continuous. Not really, you know, just Every time one little bacterium subdivides, you have a little jump. Okay, those jumps occur so closely together because there are billions of these things. Okay, there's going to be 1,000 little jumps every second or thereabouts, depending how fast the bacteria reproduce. And I don't know about that 1,000. I don't think I've heard that number. Just because it takes me that, we give you a better estimate, but it would be easy enough to do. Okay. You got a bit good problem, you know, you got a billion bacteria and they double every 24 hours. Then how many times have these things, individual bacteria split in a second? Right? How many new bacteria do you get per second? Okay. Interesting question. And not hard to understand. If you set up right, right function, and you've got it. Now, the point is, in a case like that, you have continuous compounding. Okay, so now it's kind of unfortunate. When I use N as a number of the year, but N is a natural abbreviation for number. Okay, and I used it. But the formula that you have that I think is explained in the text, but you never required to understand the explanation in any of the problems that are currently in the problem set. We're probably going to modify that actually in my courses. And I think it's important to understand how these functions are built up so you can understand them. By darn, if you're going to be an engineer, you better start thinking about these things. Okay, you're going to be better off if you start. It's not like you're going to fall flat in the face and you don't, but you're going to be better off if you do think about these things. Okay, so we're going to compound M times per year. What do we do? Now I'm working toward continuous compounding. But you split your 10% or whatever your rate is into M pieces. Okay, so each piece is 0.1 over M. If you compound twice a year, M is 2. That means you do 0.05 twice a year. 1.05 is your multiplier or your growth factor. Growth factor. You add 1 to that. And this is also multiplier. In the terminology, at least some of it. Some of the problems. In T years, you apply this MT time. And you get A of T is $1,000 for whatever your initial amount is, multiplied by this multiplier. And how many times you're going to multiply by the multiplier in T years? Well, you do M compoundings every year. So 1 year you're going to do M, and 2 years you'll have 2 of them. 3 years you'll have 3, and you're going to have M times 2 times M years. In general, this gives you going to use P for the initial amount. I'd like to use capital A sub 0, but I like P as well because it could be population or principal. Okay. Anyhow, P is the initial amount. Larger interest rate. M compoundings per year. Instead of starting with 1,000, you start with P. Instead of 0.10 divided into M pieces, you take R and divide it into M pieces and raise it to the MP. That's the formula your book gives you to bypass understanding. Now, it's not the goal to bypass understanding because not everybody, even in pre-calculus class where everybody has preparation, is going to totally understand how this is developed. But half of the typical pre-calculus class will. By typical pre-calculus class of people who have the background to understand, to really benefit from the pre-calculus course. Okay. So, yeah, well, now, the reason I go into that is because I want you to understand continuous compounding. And there's more, I'm probably going to spend pre-calculus fast. You let M approach infinity. What's that mean? Well, you don't compound every day, you don't compound every minute, you don't compound every second. You keep thinking about what you get if you compound more and more frequently. Okay, you can compound 1,000,000 times per nanosecond. But what we really do is we take a limit as M goes to infinity. Limits PE to the RT. Okay. So if you go to infinite number of compoundings, continuous compounding, in other words, compound every instant. This approaches this as a limit. So continuous compounding the amount is a function of T. Is actually much simpler expression than this, just P e to the RT. And E has a limit as n goes to infinity of 1 plus 1 over n raised to the n. You could see this as limit of 100% interest, and that's great if you can get it. Okay, 100% annual interest split up n times, compounded n times per year for 1 year. That's all this is. And that's approximately equal to 2.7. Goes on 1828, 1828, and then no more 1828 along on the top. Not a repeating. That's approximately 2.7 between 2 and 3. So that your graph of e to the t here's graph of 2 to the t, that's your basic exponential function, your tilted exponential function. And a graph of three to the t. Your graph of b to the t is pretty close to 2.7 to the t. It's going to be between 2 to the t and 3 to the t. It's not too hard to understand. But the main thing is well, okay. So make sure that's on the screen. Now, question came up about the E thing, okay? So that's a fairly extensive answer to the question, but it's a fairly complete answer. Question came about when to use log, when to use natural log. We want to make sure we understand that there's this Function for continuous compounding. Let's find the doubling time. Okay. 1,000 e to the 0.10 t equals 2,000. Our solution for t is going to be the doubling time. You think through what we just did. Within that context, we're just going to solve this equation. How do we solve the equation? Well, we divide by 1,000. Yeah. E to the 0.10 t equals 2. If we rearrange this into log form, this gives us log base e of 2 equals 0.10 t. What's log base e? It's a natural log. So we don't have to go to log C over log B. We just do natural log of C, okay? Natural log of 2 just takes one button. Again, you can do that with one button, but I don't think it's a good idea. Unless you totally understand it, then it can be a time saver. Yeah, you want to understand it. You want to understand it deeply now. If you're going to actually not be using this thing in your profession, okay? Okay, now the most important thing to take away from what we've done is fun. Okay. Adding 10% is the same as multiplying by 1.10 because of these details. You really want to understand this, understand the difference between the rate, growth rate, okay, and the multiplier or growth factor. Multiplier or growth factor would be 1.10, the rate is just 1.10. Okay. And you want to understand how those things work. So what I saw on the phone was looked pretty good, but there's a little confusion between multiplier or growth rate. Sorry, multiplier or growth factor and the growth rate. You need to understand how this table evolves. I think everybody is in a position to pretty well understand this. Then we to clarify that, this is very important to understand. When we wrote the function and we drew an exponential curve, we found the doubling time. And that's a process you really need to understand, okay? And we found the doubling time by solving this equation and this equation. Solve the equation, we had to change from exponential form to logarithmic form. Then we got into discussion about the logarithmic form, but before we did that, we talked about what it means to compound. Well, actually, so we got the doubling time from, we went back and inserted the doubling time and made a graph. If we have an accurate graph for the basic toolkit exponential function, we just replaced, this would be the 0.1, 2. And we'll replace 1 by the doubling time, 7.2. we replace 2 by the 14.4, 2 doubling times. And instead of 1, 2, and 4, we have 1,000, 2,000, 4,000. Whatever number is here, you're gonna have double that number here, and double that number up here. Then we got off into discussion of compounding M times a year and this equation ultimately, it says we split our rate into M pieces. And every year we do that M times, so we do it MT times in 2 years. And we talked about continuous compounding. You let M get bigger and bigger, which means we're compounding more and more often. And we take the limit as we're compounding continuously. And we get e to the RT. There's our continuous compounding. Told you what E is, you don't necessarily have to remember that, although maybe in pre-calculus class you do. It really should be. This is pre-calculus. And in calculus, you start out with limits. You better at least understand a little bit about what limiting means. But anyhow, we did the graph. Okay, E is between 2 and 3. So the E to the T graph is between the 2 to the T and 3 to T graph. Then we just calculated doubling time here. And this answered the question of when we use what good the ln is as opposed to the log. It makes no difference if you're solving an equation with a different base. If your base is E, then you have the natural log. Okay. If your base was 10, you'd have the log log. Okay. The natural log of E is 1, and the log log of 10 is 1. Now, one thing that you run into is sometimes authors use log for the natural log because nobody uses the base 10 log in science, except as a representation of things that grow in powers of 10. Okay, and that becomes important. So that's kind of what we did. Those are some things you want to try to understand as best you can, because they'll help you along in the future. Whoops. That's not what I wanted. We talked, I believe, about how you can take the table for your basic exponential function, your toolkit exponential function. And reverse the columns. Get the table for the toolkit logarithmic function. And we have done the same. I've done it. Sometimes I get mixed up about what we've done in the support course. Here. Okay. And we get graph. And the exponential function, and then Go to look at logarithmic function. And all logarithmic functions have graphs that look like this. You have a different base than two, and you have different labeling of your y-axis, for example. And we know, I think, that either the A equals C is equivalent to log base B of C equals A. So those are the big things that we need to understand first. And I think we've covered this, okay? And I think if you know that much, then you're prepared for the first assignment on logarithms. That'd be section 4.3. So we don't want to spend too much time talking about what we've already talked about. I want to go on and talk about some stuff that we haven't. Now, there's more what we want to understand about logs. There's some algebraic properties of logarithmic functions that are inverse, turns out, to properties of exponential. Okay. In other words, your rules for logs and your rules for exponents are inverse to each other. Now, your rules for exponents x to the a times x to the b equals x to the a plus b, and x to the a raised to the b power is x raised to the ab, and hopefully we can understand why that's true. And the remediation site that I'm working up, I've already done a whole lot with these rules of exponents. If you really want to review, it's kind of ready to go, but there are a couple of little bizarre things. And a couple of the problems that I want to go back and check some out. I think we lose one. Okay. Those are rules. Now you can have rules for logs. Now I could write log base B here. I'm just going to write log, and we're going to understand it can be for any base. Okay, so the log of A times B is the log of A plus the log of B. And the log of A to B is B times the log of A. Now, there's another rule that I've always thought was unnecessary, and it really is. Your book doesn't have, I guess it's convenient. Log of A divided by B is the log of A minus the log of B. I say this is unnecessary because these two rules imply that. So there's something that offends me about even writing this rule down, but people kind of need it, so I'm not really all that offended. So let's see. When you apply these rules, these expressions. In each case, there's an A and a B. And the form is going to match one of these. So take a minute, see if you can write down what these rules would imply. Okay, now if you didn't get this, make sure you pay attention to what I'm doing here. Log of 5x is like log of AB. Okay, which is one thing multiplied by another. Turns out I'm going to need a little more explicit about the way I write these out. So I'm going to erase these for the moment. Okay, this is a log of AB. A equals 5 and B equals X. Okay. And the log of AB equals log of A plus log of B, right? So we've identified that this log of 5x is a log of AB where A is 5 and B is X. So if A is 5, then we're going to have to put a 5 in. And if B is X, we're going to have an X here. So we're going to get log of 5 plus log of X. You want to follow this process until you've done a bunch of problems. Identify A, identify B, write out what you have. And so if we go to this second problem, we have the log of, I think it's 5 to the X, and 5 to the X. Okay. And that's a log of A raised to the B. One quantity raised to another quantity. Now again, A would be 5 and B would be X because A is the number of the base, you're raising the power, and B is the power. Base is 5, power is X. So if A is 5 and B is X, the rule says log of A to the B is a log of, sorry, because of the B, C, log of A. Now, if B is X, this is equal to X times the log of 5. We just plug A equals 5. And B equals X. If A is 5 and B is X, this rule said 5 to the X equals X log of 5. That's your result. Yeah. Then and I'm thinking. What's a log of 5 over X? We write down the rules of the 5. Log of A over B. This is the division. This is a log of A over B, which equals the log of A minus the log of B. We identify A. is the numerator and b is the denominator, so a is 5, b is equal to x. Then we plug 5 in for a, we plug x into b, and we get our equivalent expression. This is a log of 5 minus the log of x. Okay, let's take a couple of other expressions. We're going to kind of turn them around, maybe mix them up a little bit. It's a log of 7 minus the log of 3. What's the log of 15z? I don't know that. It's 5 times the log of 10, according to the rules. The log 7 minus log 3 is this. So you have the rule. And I'll write the expressions. I've switched the sides because I want this expression back to this. A equals 7, b equals 3. So replace a by 7 and b by 3. And you get the log of 7. Again, after practicing these and doing a couple dozen of them, you get the hang of it, and that's already happened. It was a quick sum. Okay, log of x plus the log of y. Well, we identify that we got this. You got the log of a plus the log of b. And the rule says I think it's log of a times b. So a x b would be y. Then log of a b would be the log of x y. Or it's combination, I do know what's that. Okay. And then 5 log 10 v log of a is a log of a to the b. I think I saw an error in this. So again, if you get into the homework and you're getting them right, you're probably doing fine. If you miss one, come back and write it out the way I'm telling you to write it, and it will become clear to you. I can see if that's going to work for everybody. Okay. So B is 5. A is 10. So let's see, A is 10, so it's going to be the log of A to the B. A is 10, so they get the log of 10. B is 5, 10 to the 5th. And there we have these expressions. Now this one is a little more complicated, of course. You can see it if you're looking at the camera. It's there. And that's this far. Okay. So now we got the log of x squared y cubed over z. So I can break this down. There's a division, so this certainly fits the log of a over b form. Well, a is the numerator, which is x squared y cubed, and b is the denominator, which is z. So this is going to be the log of x squared y cubed minus the log of z. All I've done is identify a as the numerator, x squared y cubed, plugged in for a, which gave me log of x squared y cubed, and then my b is the denominator, that's just z. So we substitute that and we get minus log z. But there's more. We can simplify this. Log of x squared y cubed minus log of z. The log of x squared y cubed is again log of AB with a equal to x squared, b equal to y cubed. Now, I'm not going to write out the rule explicitly. You can do that as scratch, but it's going to get a little long and complicated if I write out all the details. I think everybody understands now. If you got a log of this times this, it's a log of this plus the log of this. So that's going to be the log of x squared plus the log of y cubed minus the log of z. Then you get the log of x squared plus the log of y cubed minus the log of z. And that equals, I'm not going to write out the rule, because I have to write it out twice. I have to write it out for this and this. But if you're used to the rule, you know the log of a to the b is b times the log of a. This would be 2 log of x. And this would be 3 log of y. This would be log of z. So we can write out the final result. The log of x squared y cubed over z is then 2 log of x plus 3 log of y minus log of z. And after you've done a few of these, it becomes natural to just be able to look at this and say, well, this is multiplied, and this is multiplied, so the log of x squared is 2 log of x, log of y squared is 3 log of y. You start being able to see it and do this very efficiently. Okay. So you can see that a little more, you know, but you're going to see exactly the same rules applied in exactly the same way in the text and in the with the problems. Okay, now I want to solve an equation. We're gonna make these base 2 logs. The rules apply if you put a base on, you just keep that base there. Okay? So how would we go about solving this equation? Well, I'm going to demonstrate. I'm going to ask you to try to work it out, although I think you could. By the first rule, I have a log of this plus a log of this. It's a log of this times this. Okay. Now, how do we solve this? We change this to exponential form. Doing what we did just a little while ago. We see that this means that this is like b to the a equals c. This is, this is log b of c equals a. This is b to the a equals c. I'm gonna write that down. This is log base b of a equals c. This is b to the c equals a. Now, can you solve this equation? I'm going to ask you to do it. Take a look at it. You think you can solve it? Well, if I remind you what to do, you're going to solve it. What kind of an equation is this? A quadratic equation. You multiply these out, you get a quadratic. Okay, and of course, 2 to the third is no mystery. 2 to the third is 8. If we multiply this out and you use the distributive law, 2x times 3x minus 2, 5 times 3x minus 2, and all that stuff, you get 6x squared, you get 15x minus 4x, that's 11x minus 10. How do you solve that? Put it in the standard quadratic form. Standard form of the quadratic equation. We have this. And you might try to factor that, but I don't think you're going to get very far. It doesn't look to me like it's going to factor. I could check the discriminant and get 121 minus. It happens. 116, 72 is 532. This would be the square root of 532. It's not a perfect square. 525 is, 576 is, 532 is. So you don't have a perfect square, you don't have something to simplify all that easily. It's best just to go to a quadratic formula. You don't even bother trying to find the quadratic factor. Okay, now you could also use long division as a rational theorem, and maybe something would come out of it. But it's so easy to use a quadratic formula, and it's not easy to factor that. They can go to the quadratic formula. Okay, now what do? We started with this mysterious looking equation, and we did the obvious thing. We have a log of something plus a log of something. That's the log of something times something. a rule that you get used to rather quickly. Then we change that to exponential form using log base b of a equals c is the same as b to the c equals a. Excuse me. And that change is very straightforward. Everybody doing that pretty well, okay? Which about you apply that rule. Then just using the distributive law to multiply this out. Subtract 8 from both sides, you get this and use this, and I'm not going to go through the rest of it. Okay. So we've combined 3 or 4 things. And what turned out to be a pretty simple matter. I don't think we'll have any trouble doing this in the homework. So you have problems of this nature. Okay. And it doesn't get any worse than that. Now, there's an assignment that's due Wednesday, an assignment that's due Friday. And you'll see this kind of stuff in the assignments due Friday. And these rules. Once you have that down, you're pretty good with logs. Now, there's more. And it's something we'll probably talk about next time if I see people have trouble with it. But I think you're going to pick it up from the open math, so we'll try to address the things I think you might have trouble with. And if I'm wrong about what you have trouble with, well, we'll talk about it. In other words, if you have trouble with something I don't think you're going to have trouble with, we'll talk more about it. Okay, I started out. I didn't record, but we look at the domain and range of the exponential function so we can understand the domain and range of the logarithmic function. Okay, remember, we got the log function, it has a graph that looks like this. From the exponential function, it has a graph that looks like this. The domain of this function, if we just restrict ourselves a table, it just goes -2, -1, 0, 1, 2. But of course, we then sketch the smooth curve, and now the domain of what I've graphed here would be all numbers from -2 to +2. We can extend this. We go to 3, 4, 5, 6, 7, 8. Every time we add an integer here, we can write another integer in this column, we're going to have to double this. And these numbers always double. Start with the fourth, you double it, you get a half, you double that, you get 1, you double that, you get 2, you double that, you get 4. You get 4, and you keep doubling. There's no limit to how many times you can double. There's no limit to how big these numbers get, and they get really, really big, really, really fast. By the time you get out to 10, you're up to 1,024. By the time you get to 20, you're up to 1,050,000, something like that. Okay. The numbers get huge, really fast. Well, there's no positive number that you can't put in here and get a result. And so we're going to look at the domain. Any positive number is okay. We can always double the last number. Basically. Any negative number is okay too, because what happens if you go in this direction? Oh, to get this number, you cut this one in half. This is half of this, this is half of this, this is half of this. And every time you write down another negative number, but in the negative direction, you got to take half. Well, you can take half forever. Well, you can't because you don't have forever. Okay, but if you did have forever, you could do it forever. You do it as long as time keeps running. Okay, so it's like you have a number that's this big, take half of it, it's this big. Take half of this, it's this big. Take half of this, it's this big. Take half of this, you keep taking half. Okay, if you keep taking half, you're never going to get to my hand. You're going to get really close. You got to get so close that the atoms will start merging. So I guess maybe you do get to my hand, but theoretically, if this is a point here, and you're taking this point and always moving this point twice as close, points have no dimension, you keep getting twice as close forever. So these numbers can go all the way to approach negative infinity. So your domain is negative infinity to positive infinity. Now, what happens to your y value? Well, we've seen you keep doubling these numbers, they get really huge really fast. Okay, that approach infinity. What happens with these numbers? Well, if we're getting. What are we getting twice as close to? We're getting twice as close to zero. Okay, 2 is twice as close to 0 as 4, 1 is twice as close to 0 as 2, and so forth. So we're approaching 0, but we never get there. The y values never get to 0, they get close. So the range is a open interval 0 infinity. And we never get 0 in this column. Negative numbers, these numbers get really tiny, just like these numbers get really huge, go in this direction. But they never reach 0. They never reach infinity in this direction either, but they approach infinity. And these numbers approach 0. So there's the domain and range. Okay, well, it's kind of a no-brainer now. If we reverse these columns, the domain of the exponential function becomes the range of the logarithmic function. So logarithmic function, well, let's look at it. Here we have the graph. Okay. The range is a set of y values. What happens to the y values? Well, the y values appear to be, well, we appear to have an asymptote. Okay, means y values keep going down forever. So the y values can go all the way to approach negative infinity. And then the values here, it's not as obvious if this thing doesn't level off, but it's very clear that these numbers could be any positive or negative number, because these numbers can be any positive or negative number. So the domain is the open interval 0 infinity. Range is the interval negative infinity to infinity. So you can take the base 2 log of any number as long as it is 0 or negative, as long as it's greater than 0. That's what the domain being 0 infinity tells you. The range, you can get any number from 0, from negative infinity to infinity. Any y value is possible. It's kind of important to understand that. Now, one reason it's important to understand that is you might be asked to find the domain let's say we want to find the domain and range of y equals f of x equals log base 2 of 3x minus 12. Domain of the log function is 0 to infinity. You can only have numbers in here that are greater than 0. So, quantity you're taking the log of is 3x minus 12. has to be greater than 0. We can solve that equation. If I that x has to be greater than 4. So domain is equal from 4 to infinity. If you put 4 in here, you're going to get 3x is going to be 12. 12 minus 12 is 0. You can't put 4 in here and get anything because you can't take the log of 0. Goes back to the fact that the exponential function can never be 0 and the inverse relation. So they understand that, yeah, more or less challenging point. You just got to know you can't take the log of 0 because the graph of the log never reaches the y-axis, never reaches where x equals 0. Bottom line, the domain of log functions from 0 to infinity. So whatever's inside here has to be greater than 0. You write that down as an equation, you solve it, and you get within that. There's a range. Negative infinity to infinity, right? I think we need to be a little more specific. We're talking about the domain of f of x. When I say the domain of the log function, that means the general log function, one we just talked about over here. Okay. The range of the log function is negative infinity to infinity. The range of this is also negative infinity. Okay. We'll have problems with that nature in some. How would you graph y equals log base 2 of x plus 3? I'm going to tell you. Just going to do with a picture.
Yeah.
How is this graph going to compare to the graph of the log base 2 of x? Going to be horizontally shifted negative 3 units. Because x, for this function, x has been replaced by x plus 3, and we can have a horizontal shift of negative 3 units. So graph is going, the whole thing is to the left of the x-axis, okay? So we take every point in this graph, and I'll just pick the points, correspond to x value 1, 2, so forth. No, we picked a little more. As we do it. Not very good. As we do it. Okay, so we take this point and move it over 3 units. We take this point, and move it over 3 units. We take this point, and move it over 3 units. Do this with all the points. And there's no gap. In other words, we use transformations. If you see a graph in the homework that looks like this, when you don't have all this, you have, see a graph that looks like this, you can pretty much estimate where the asymptote's going to be. That tells you how much it's been shifted. Not might be stretched or compressed. And you have videos that help you with that. If you understand transformations, you're not going to have too much trouble with this. If you don't understand transformation, you probably would. So you should at least be able to do some basic transformations, like what would we do to get y equals 2 log base 2 of x plus just plain old x. We'd have to move every point twice as far from the x-axis. Okay, so we want to have some basic. With transformation. I want to say that there's not a whole lot in homework that requires transformations. But yeah, maybe 30% of the homework on this third assignment will require some transformation. But yeah. The graph. The actually, I don't want to get into it. We should do horizontal vertical transformations. So let's just do. Yeah, 2 times the log base 2 of x. So here is y equals log 2 of x. Need piece of chocolate. I'm not finding it. Many ways to construct this graph. I like to illustrate it with arrows. If we do 2 log base 2 of X, that means Y for this function is going to be twice as big as Y for this function. Okay, these arrows represent the values of Y for this point, this point, this point, and this point. We don't have an arrow in this point because Y has a value of 0. An arrow would have to have some length, it wouldn't have length 0. And it comes with a little X thing. Okay, well, how do we construct a graph? Y 2 log base 2 half of X? We double the values of Y. To double the value of Y here, we add an arrow up here that's got the same length as the arrow down here. To double this value of Y, we have an arrow of the same length. There's the one that represents Y. And we do the same thing here. And the same thing here. And now we have the tips of these arrows. There we have it. Now, if we want to do a reflection or one thing or another, we can easily not do it. Now, for some reason, I mixed up the order of the assignments. I'm not going to change the order. That's sections 4.3, 4.4, and 4.5. But I've got section 4.5 due Friday and section 4.4 not due until next month. Okay. So if you want to do them in the order that they're presented, 4.3, 4.4, 4.5. Go ahead. I think maybe I had a reason for doing that, so I'm not going to change it. But I don't think it makes much difference what order you do 4.4 and 4.5. One doesn't depend that much on the other. But there might be a little more dependence than I think there is. Okay. So use your own judgment. If you do it 4.5 first, and you find that you kind of get stuck, you might want to go back and do 4.4 or 6. Nothing we didn't talk about today, but you do need to get your hands on and practice it. Okay. So I'm going to kind of recommend that you do them. You do 4.4 before you do 4.5, just to make sure you don't mix it. Matter of fact, I'm rethinking it. I'm going to go ahead and switch. I can't think of a good reason why I had them in reverse order. I think when I was switching assignments around, as I had to do so, I'm just smashing. Maybe I just got careless. So I'm going to put them in order. No other assignments are in order. Just take a few seconds to change. But if there are any questions, let me know. If not, I'll dive into the assignments. These are not particularly, most of the problems are not particularly challenging, but you do want to get used to the rules and so forth. And you might find them more challenging than I think you will. So we'll see how you do.